You remember we did something like this in the first part of the beginning, explain derivatives, probably something similar. Now, this is x plus x plus delta x. The difference between them is called what? Delta x, yes. Difference between them is going to be called delta x. Remember, delta means a difference. And between f of x and f of x plus delta x, what is the difference? What is it called? Just delta y. Delta y. Change in the y-axis. Okay? Remember that? Yes. Okay. Now imagine that based on the point x, f of x, I'm going to draw a tangent line. Tangent line, you remember, touches one single point, which in this case is going to be this. That tangent line. All the way up until it touches the projection of this. Okay? This is going to be my tangent. Now, if I have tangent line, how can I get the slope of that tangent line? Would be from here and this one. Okay? The slope of the tangent line is the inclination of the tangent line. Yes? So to get the tangent line and the slope for that, we need to get a value for this part and a value for this one. If you observe, this value here is exactly the same value as this. And they represent the same change. But in this topic, this change is not going to be delta x anymore. It's going to be called dx. Why dx? In this case, d means differential. And what does differential mean? Differential means a small change. Okay? So it means that if this value, dx, is a change on x, and this value is delta x, it's also a change in x, but for the graph, then delta x is going to be equal to dx. Changes in the x-axis. Do you get that? Yes. It's just a notation. Yes. Just a notation. It means a change. But in the case of the y, this change in y for the tangent line is not going to be called delta y, but that's for the function. For the tangent line, it's going to be called dy, which is going to be called the differential of y. What does it represent? Small change in y. My slope of the tangent line is going to be then what? Dx over dy. The y over dy. Dy over dx. Okay? Changing y for the tangent line, changing x for the tangent line. And if you remember, from the first partial, the slope of the tangent line is also equal to something else. Remember? The derivative. Very good. What does that mean? That if this is the tangent line, the slope tangent line, and this is the slope tangent line, those two are going to be equal. So the derivative is dy over dx. That is going to be my formula for this. Okay? So basically, the derivative of a function is always equal to what? To dy over dx. And what does that mean? D represents small change, small difference. That's why it's called differential. Do you get that? Okay? And from this one, from this same formula, we can also isolate one of the variables. Which one? This. So dy is going to be equal to what? It's a division. So it's going to be the derivative times dx. This is the differential of y. This is my derivative of f, and this is my differential of x. Is that there? Yes. Yeah. Let's do some examples. For example, let's say I have a function which is y equal to 5x to the cube. Another one, f of x equal to 2x to the 4 power plus 2 sine of x. And another one, which is square root of x plus 1 over x. Okay? I have these three functions. The question will be, find the dy. What do I do? Apply the formula. Here, dy is going to be equal to what? The derivative of the function times dx. What derivative of this? 15x square times dx. That's it. Yeah. Now, it's not the end of the topic. Okay, another one. I want to find dy for this one. So, the derivative of this? X cubed plus x times dx, but for everything. So, times dx. The last one, dy, but before that, do I need to rewrite this? Yes. Yeah. So it's going to be x to the 1/2 plus x to the minus 1. So it's going to be 1/2 x to the minus 1/2 minus x to the minus 2 times dx, and then I write. Pleasure. Times dx. That's it. The only difference between this one and the derivatives is now it's just a single part. The dy, the differential, equal to the derivative times dx. The end. Questions so far? A little paréntesis here. De hecho, este tema antes era el primer tema de mate 6, porque esta es la introducción, lo que sí que son las integrales, una antiderivada y luego integral, ¿sí? Pero lo metimos ahora como mate 5 porque pues tiene que ver con derivadas. Y aún aunque ustedes escojan toma de decisiones o cálculo integral, van a tener que usar esto, porque también en toma de decisiones van a ver integrales más sencillas que en cálculo.
¿Lleva cálculo 2 o no, profe?
No creo.
¿Profe, usted va a dar cálculo?
Que no.
Las integrales podría decir que es lo opuesto de
la antiderivada, sí. Pero para poder integrarlo, tienes que primero ponerlo en su forma diferencial. Lo pones en forma diferencial, lo integraría con dx y ya me queda la función original más una constante. Entonces por eso vemos esto. Antes de ver integrales, vemos esto.
¿Y cómo puedes sacar la constante?
Con condiciones iniciales. O sea, ya cuando vimos lo de las gráficas de cuándo es máximo mínimo, no sabía dónde estaba el punto real de la gráfica, que necesito más condiciones. Te las daría el problema, pues, por ejemplo. No voy a dar cálculo, no creo. Todavía no me dicen bien, pero...
No nos abandone el problema.
No, se lo da Tiberio.
¿Hay cálculo B? ¡Ay, carajo!
Por cierto, luego voy a preguntar si alguien quiere entrar a hacerle Tiberio para que se abra el grupo, porque es el mínimo 20.
¿Quiere ganar?
Ya me voy. Que sí, que no, y ya les digo el Tiberio y ya me dicen.
Profe, de casi
es como de la materia de la realidad. Pero aparte de que un certificado que sirve para que lo estudiaran en el extranjero, por ejemplo, Estados Unidos, es inválido el certificado. El APN con esto. O sea, todas las prepas que estaban en AP, y hay AP de muchas cosas, de matemáticas, de Fine. Okay. Good. Can I continue?
Yes.
Okay, so far then, derivatives, done with explanation. Differentials, done. Here it says Leibniz notation. What do I mean by that? Actually, this formula, this is called the Leibniz notation. Just for your information, Leibniz was a mathematician that developed derivatives. Along with some yeah. That Leibniz one person, Newton was the other person who developed derivatives. In different places, different years, but they developed derivatives. So you want to tell someone what derivatives? Okay. Now, the last part, linear estimation. What do you mean by linear estimation or linear approximation? In this case, imagine this situation. This function here is a simple function. It's like a parabola, right? But actually this function could be any function. It could be a complicated function. For example, an exponential or a big polynomial function. Actually, if I were to get this value of the function, I will need to evaluate this in my function, right? So imagine that this value is, I don't know, let's say 5.9. And this function is a complicated one. So if I want to evaluate, I want to use the calculator and all of that. But the idea of this procedure is that we could change this function into a line. Approximate that into a line. And if I change this into a line, I can get a value on that line that is going to be an estimation of the real one. Okay? How do we do that? Using derivatives. In this case, the drawing is not that clear because the difference is too big. But actually, when we apply this, is with very small differences. So the idea of this topic would be to estimate this value by applying the value in the tangent line, by using derivatives. That's the big idea. Okay? Again, another parenthesis. En física, ¿en qué van, por ejemplo, ahorita? Potencial cinética. Bueno, antes que estudiara física, antes de varios años, había un tema que se llamaba expansión térmica, thermal expansion. En el que, por ejemplo, tenían una placa de metal, la ponían al calor y pues se expande, ¿no? ¿Sí? Y las expansiones son expansiones muy chiquitas, no se expande así que, enorme. No, o sea, son muy imperceptibles, o sea, son errores que cambian así de a poquito. Esos pequeños cambios, yo hubiera podido estimarlos usando derivada, porque la derivada me permite estimar cambios muy chiquitos. ¿Sí? Eso, para eso me sirve. Eso lo vean antes, ya no lo ven ahorita, pero en física sí se ve también eso. Pero entonces, maestro de física, ¿quién es Dago? Pues Paul sabe. Pregúntale.
¿Y quién lo sabe?
No, Paul sabe. No, debería saber. En fin. Okay. Let's try an example to see what I mean. Can I erase this?
Yes.
Okay. Ready? Can I continue?
Yes.
Okay. Example. Let's say that I want to estimate the answer to this expression. I know the calculator is easy and fun and that's it. But the idea is to apply derivatives to estimate a value for this. Okay? First, first step for this. No, we're going to graph it in. But first determine or define a function for the expression. If the expression is a square root of 4.8, what could be a function for that expression? Square root of x, yeah. The function is f of x square root of x. If it was something like 4.8 to the square, it would be x squared. If it was 1 over 4.8, it would be 1 over x. So the idea is to put a function that represents that expression. Yeah? Now, define values of x. In this case, we're going to find not just x, will be x. We're going to find also dx, delta x, and x plus delta x. Okay? The idea of this is that we're going to find every element of the graph that we did, and then we're going to graph this. So we need to find all these elements. The function is square root of x. So what will be my value of x? And no, it's not 4.8. The idea is to use for x a value that can be found directly from the function without using the calculator. So we're going to try to put x as an integer value that is the closest to this one, and that can be done now. That can be done exactly with the function. 4 is better. 3. No, 3 no. Why not 3? Why not 5? 5 is the closest, yeah, but square root of 5 is not exact. So the idea is to use an integer value that can be done with the function and gives me an exact answer. So 4 is the best. dx. dx will be the difference between this one and that one. So 4.8. 4 or 0.8. Delta x is the same as dx. Remember? Delta x is the same as dx. So it's going to be 0.8. Remember that. dx and delta x are always the same. Subtraction. The one that I have minus the one that I got as an x. Subtract. 4.8 minus 4 is 0.8. Okay? Now, x plus delta x is the one that I have here, which is what? 4.8. Okay, so far? I can't finish, huh?
Y si no tuviera el square root también sería igual, o sea que si fuera más 4.8.
No, if it was, for example, not square root, if it was, for example, this to the square, then 5 will be better.
Okay.
Because 5 to the square is an exact number. Yeah? In this case, I need to choose the 4 because the square root of 4 is exact, or square root of 5 is not.
Porque en ese tu dx sería menos, ¿no? Menos .2.
If I choose 5, yeah. If I choose 5, yes. Okay. Can I erase this?
Yes.
Okay. The next part. Calculate values of the function. dy f of x plus delta x, and delta y. Okay. We got the values from the function. Now we're going to evaluate the function to get those values. dy. How can I get dy?
dy equal to f graph of x times dx.
And dx, yes. The function is this one, so dy is going to be the derivative of that one, which is what? 1/2 x left and 1/2 times dx. If I rewrite that, it's going to be 1 over 2 square root of x dx, right? Now, listen, now I have values. Put the values in my differential. So it's going to be 1 over 2 square root of 4 times dx, which was 0.8. How much is that? Help me with that, please.
Mr. Y 1/2 of x.
The derivative. What's the value?
A ver, por los 80.
.2? Okay, very good.
Profe, está bien si lo dejamos un poquito.
No, it doesn't. You need them to compare and see it, so you just. Okay. F of x is the function, say. F of x is the function evaluated with the value of x, which is the square root of what? 4 equal to 2. F of x plus delta x is the function evaluated with x plus delta x, so square root of 4.8 equal to what? Use the calculator. Use the calculator.
Pero ¿por qué con la raíz?
2.19.
Pero el futuro no usa la función.
Give me more decimals, please. 6 decimals.
0.8, 90.
Okay. Before I continue, before you ask, why do I need to do this again if you told you that I need to do all of this? Yeah, I know that. The idea of this is at the end comparing the values. We're comparing what happened with the real answer and the estimated answer. Okay, that's the reason of this. It's not that I can do that with a calculator. I can. It's this. Yeah, but the idea to find everything else is to compare the estimation. Do you get that? Not necessarily. We'll see. Delta y will be what? No. How can I find it?
Le resta puntos.
F of x plus delta x minus f of x, no? From the graph that I did. It was f of x plus delta x minus f of x. So I need to subtract this minus what? Minus this. So it's going to be 0.19089. Do you understand why?
¿Y esa es la aproximación?
Huh? No, I haven't finished it. I haven't. Questions so far? No. No. Okay. The last part will be to graph. What do I mean by a sketch a graph? The same graph that I use to explain, you're going to do the same for this example, and you're going to plug all the values. So, in this case, the function is what? Square root of x. What's the graph of the square root of x?
Cállate, cita.
Okay. What's the graph of square root of x? Have a parabola, yeah. Now, listen, in this topic, I don't want you to get the exact graph for that. It's just a sketch, so the shape will be enough. So the graph for that is, yeah, it's going to be, have a parabola, you can do it like that. No need to put the values in there. The exact values are not enough. But, from here, we're going to put all those values in that sketch and see what happens. It says x equal to 4. So here, x equal to 4. The next one, x plus delta x, is going to be, put it on the right. So it will be x plus delta x equal to 4.8. I know that this is too far from this one. I know that. But the idea is to represent what happens, not to put the exact values. Do you understand that?
Yes.
No? No.
Yo.
Ok. La idea de esto es que voy a graficar esto, lo voy a poner en mi gráfica y ver qué pasa. Pero no quiero la gráfica exacta, perfecta. Aquí no pasa nada. Por eso aquí ya voy a poner simplemente los elementos, como dice al principio con la explicación. con la gráfica, o sea, lo mismo pero ya con valores exactos.
¿Y por qué esa línea?
Porque esa es la gráfica de una raíz de x. O sea, no la quiero exacta, pero la quiero como es. O sea, si es una raíz de x, pues debe ser así. Aquí puse el 4 y otra es 4.8, pues lo pongo a la derecha. ¿Qué tan lejos, qué tan cerca? Ustedes dependen. No lo pongan tan pegado, pónganlo que se vea a una distancia que se vea. Ok.
¿Y por qué la puso así de la gráfica? Si le ponen
Ah,
la gráfica.
that's the graph for that.
Ah, ok.
That's the graph for that function. If it's x squared, it will be different. Okay. Between them, what's the difference? Delta x is equal to dx is equal to 0.8. Yeah? Then, if I project that, what do I have? F of x, which is what? 2. If I project that, I have what? F of x plus delta x, which is 2.190890, and between them, delta y is what? 0.190890. Okay?
Okay.
Now what? The tangent line. From where do I put the tangent line?
De la F de X.
Aha, from x, f of x. Tangent line all the way. So at the end, it crosses with this projection here. And as long as a tangent line and it touches one single point, doesn't matter.
Pero puedes hacer tu tangent line más abajo.
¿Puede ser para abajo o tiene que ser
Ah,
para
that,
abajo?
no. A tangent line only touches one point and goes over or below depending on the graph. So if you put it like, for example, the graph is like this and put like this, is not a tangent. The tangent has to only pass a little to the point and then go until it touches this and forms a triangle. Now, from this one, from the explanation that I gave you, which one would be dy? Where is dy in this one? From this to this vertical. This part of the triangle. That's dy. Which is what? How much is dy? 0.2. Okay? Do you get that?
Yes.
What does that represent? What does that mean? This is my estimated change, and this is my real change. Which one is bigger? In this case, it's dy, because it's 0.2, so we're fine. And the real one is 0.1908. So it's an estimation. The estimation is bigger than the real one. And lastly, we need to find this point here, which is going to be called the value of estimation. BE. How do I find that? What formula would be to find this point? I don't have the equation of the tangent line. I don't want it. From the graph, you can tell me, how can I get this point?
dy plus f of x.
It's okay, very good, that's it. F of x plus dy. Do you understand why?
Yes.
This is f of x. This is dy. This plus this gives you this one. So it's going to be 2 plus 0.2 equal to 2.2. That's the value of estimation. And that's it. What does that mean? It means that if I were to estimate the answer to that using differential, that's what I get. But the real one is 2.19 something. But this is the estimation. Do you understand?
Yes.
Bien. Es mucho procedimiento, yo entiendo, pero lo que quiero es que me entiendan por dónde va todo el asunto. ¿Sí? O sea, por dónde va el asunto. La idea es de que, usando una tangente, estoy estimando la respuesta a una operación. Si me dicen, ¿por qué esto no se hace con calculadora? Sí, lo sé, pero a fin de cuentas ya estimé este valor, que me dio que era más grande que el real. Que puede pasar, pero no por gran cosa. entienden?
Sí.
Sí.
¿Alguien no me le foto y mande la foto?
Gustaron, o sea.
Yo sé que...
Okay, fine.
Ah, no, todavía no.
Tomorrow we'll see more examples for this topic. Okay? It's the same procedure. Very good.
A ver, manda salir.
Okay. If there are no questions,
¿Qué más, Rodri? Manda besos a las chicas, a las chiquinenas.